right, well, I suppose we'll get going. So I kind of mentioned that, well, we didn't have class on Monday, which kind of throws the schedule off. So I was like, okay, well, what can I do? Well, I have a topic that kind of fits into one class day that I can talk about. It's recursion, so that's what we're going to talk about. And it didn't take the whole class period, and everyone had time to work on the quiz, and everyone handed it in the other class. So that's a good sign. That means it was an appropriate amount of time. I guess I don't have any announcements at the moment. Other than when is this quiz due? I don't know yet. Saturday at the earliest. But since we're kind of only starting it like today instead of having the Monday and the Wednesday, I don't know. I might make it do like Monday at midnight or something, so that if anyone has questions, they can ask me questions on the Monday. Because six of one, half a dozen of the other. And the next topic we're going to work on, I need to make the notes for, so I hope we all like it. I will be asking after the fact, hey, did you... Okay, it's hard for me to say, did you like this? Because asking that about math, most people are like, no. But I'll say, did you hate it a lot? Like, did it make no sense at all? Or were you like, yeah, I mean, I kind of got it the same as the rest. And I'll be like, okay, well, at least it's not, like, ridiculous. But anyway, the only other announcement, I guess, is all the quizzes are graded. I'm working on the assignment. Should be posted in the next day or two, the grades. There's nothing to say about the quizzes. Everyone did fine. Good, even. So, yeah. Which is usually how it goes in this course. People hand stuff in, they do well. So last class, we finished off our conversation about set theory. We talked about how the operators sort of interact with each other, right? Like there's distributive properties and stuff like that. We get essentially algebra with these set operations too, because they're based on logic operators. And then I defined this Cartesian product, A cross B, A times B, which is just a set of ordered pairs or tuples, where the first thing is in A and the second thing is in B. So nothing too fancy there. I gave some examples, like the weird one I constructed, and then also R2 and R3, which is the plane and 3D space, respectively. So there's some familiar examples there. Okay, so we're going to start talking about recursion. Did you talk about recursion at all in Python or no? I don't think you do. Okay, good. Because I come at it from more of a mathematical perspective, but it turns out there's a lot of overlap there between programming and math, because the definition is the same either way. It's just there are recursive math algorithms and then there are recursive computing algorithms. So let's start with the definition of what this word even means. So recursion is one of those things where initially it seems overwhelming and challenging, but it turns out most of the time when we actually like break it down, our brains work this way anyway. So a recursive function refers to itself in its definition. So in terms of programming, it's a function that calls itself, right? That's the math version is a function that refers to itself in its definition. The programming version is a function that calls itself. So that's the base definition. There's a bit more to it, but recursive definitions are kind of everywhere. They're all over the place. I would say, when I say it's kind of how our brains, operate, it's common for business rules to be given to you in a recursive definition. So what leads to a recursive definition? Well, you have some problem, it's this big, and then someone says, okay, you can shrink the problem in half. Now, if you just do the process on this half, and then do the process on this half, and then combine them at the end, then you've saved your work, right? You've saved work. So that's what recursion does, right? It takes a big problem, splits it into smaller pieces, and then tackles the smaller pieces. But that usually means now you've got the smaller piece, and then we do the same thing again. You got the smaller piece, break it up into even smaller pieces, and then eventually you stop and then work your way back up. So recursive algorithms are kind of everywhere. Now, I would say often, not always, but often, recursive algorithms, by the nature of take big problem, make it smaller and simpler, are easy to implement, with quotes around it. So in terms of programming, that means there's very little code to actually build. And in terms of math, it just means they're usually easy to just look at and go, I understand what I need to do based on this algorithm, right? But hard to debug because a function that calls itself a whole bunch of times is a nightmare on the stack. So you just like call itself a bunch of times and you're like, something went wrong. Where did it go wrong? I don't know, right? Because there's 100 calls of the function being made. Which one did it break down on? Hard to find, right? And even if you're using like PyCharm's debugger, it's like a nightmare because it calls itself like 100 times. So you're stepping through it. When does it break? Hard to see. They're hard to debug and inefficient. And oftentimes this is inefficient in terms of memory used with computers, right? Because a function is calling itself a bunch of times. Every time it does that, that adds memory, right? It's storing stuff. So you're using a lot of memory to do this, whereas you could maybe do it in place or iteratively and not use nearly as much. Also, in addition to this, every recursive algorithm can be done iteratively. So that's without recursion. And so there's a reason for that. Has anyone heard of a Turing machine? Okay, so if you don't know, a Turing machine is basically the most basic form of a computer theoretically, right? So that Turing machine does not have functions, but it can still do all of these things. So if you can implement this algorithm recursively by calling itself, this isn't even really a computing science result anymore. This is more of a math result. That same Turing machine can also do it iteratively, which means you never need to use recursion. You can always avoid it. However, that's in theory. In theory, you can avoid it. In practice, sometimes that comes with a lot of problems. The most common example I can think of is merge sort, or well, most kind of sorting algorithms actually. So there's it calls itself recursively to do it when you're doing this this sorting algorithm, and you can do it iteratively, but the trade-off is it's a nightmare to maintain. It's way more code. Like we're talking a lot more, and it uses more space because just the nature of the way it works. Because the recursive one can kind of do it in place, whereas the iterative one has to create a new array to sort of manipulate. So it can't be done. It needs more space. And also, again, it is a living nightmare to maintain. So like, go look up like sorting algorithms iteratively and or without recursion, and you'll be like, ooh. I don't remember the name of the other sorting algorithm that's like that. But there's a couple that are generally implemented recursively, and if you try to do them without recursion, it's bad. But can be done. So this is like one of those the math things where we have a lot of theoretical results that say, yes, this does exist. And then your next question is, okay, well, show me. And I'll be like, no, I can't easily. I'm sure we can find it, but I don't know it. But I know it exists. So this is another situation like that. But because recursion pops up everywhere, and as programmers, you live in the real world, where you have a 2-week sprint and your boss says, hey, I need this implemented in 2 weeks. It has to be done in 2 weeks. And you're like, well, I could think of a clever way to do it, and it would take me a month and a half, but I have 2 weeks. So recursion it is then. And then that's it, right? You do the inefficient way because you are a human being with time constraints. So I don't want to say never use recursion because it's inefficient and hard to debug. Sometimes it's just the reality, right? You have time constraints and you just do it recursively. So because this is a section on recursion, all the things I'm going to present to you, there are very easy ways to do them iteratively. You do not have to do any of these recursively, but for the purposes of demonstration, we are going to do them recursively. And you'll see it in the first example I have. You'll be like, wow, that recursive definition is actually worse than the original definition. And yeah, I know, but it's for explanation. So let's give some examples of recursion. So the first one is regarding the factorial. So the factorial of a whole number so it's this an exclamation mark. So what we do is we say, okay, take n and then just multiply it by every number preceding it. So we've got n times n minus 1 times n minus 2 times, and we keep going until we get to 3 times 2 times 1, right? So just take whatever number you're at and multiply it by every single number that comes before it. We also have sort of a situation here because if we look at how this is defined, okay, multiply every number before itself. Well, there's no number before 0, and this seems to stop at 1, because if it went to 0, then n factorial would be 0 no matter what every time, so we don't include 0. But whole numbers include 0, so we need to say, well, what happens when we do 0 factorial? There are deeper theoretical reasons for why we say it's 1, but for the purposes of this, it's convenience, right? It's just really convenient to call it 1. But if we look at the gamma function, this is also, it makes sense with when we expand factorial to not just be whole numbers. So there are the reasons for that. Okay, so just as an example, if we had 5 factorial, so this is going to be 5 times the number before it, times the number before it, until we get to 1, and then we stop, right? So that's 120, right? So if you haven't seen factorial before, it's one of the fastest growing numerical functions. So I don't know if you've talked about it in any of your classes, but maybe you've seen it in passing, talking about certain algorithms having algorithmic efficiency, big O notation. Have you seen that at all? Have you heard that anywhere? Okay, that's fine. But the point is, you can think like n squared. It gets pretty big, right? N cubed gets bigger faster, right? Like if you have 2 squared, that's 4. If you have 2 cubed, that's 8. So obviously cubing gets bigger faster. And then if you did n to the power 4, that's going to get bigger even faster. So we sort of have, where do I want to write this? Like n squared gets big pretty fast, but then we can also have like 2 to the n, right? Which gets big really fast, right? Like if we just think, if we did 5 squared, that's 25. 2 to the 5 is 2 times 2 times 2 is 8, 16, and then 64, 32. So already at 5, 2 to the n is bigger, right? So it gets pretty big pretty fast. N factorial, so for 5 factorial, was 120. That's way bigger already. So n factorial grows really, 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 really fast. If someone says, if you just hear in passing, like at work or just in a class or something, or you're reading something, and someone says, yeah, this algorithm runs in n factorial time, you're like, wow, that's bad. That's like, if I run it on an input of like 10, I'm waiting minutes for it to run on 10. Whereas for n squared, it's like, oh, well, it doesn't, like, it's going to be fine. So n factorial grows really, 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 really big, really fast. And there are some algorithms that actually are, our best case is basically that, like the traveling salesman problem. If you try to solve it naively, is n factorial. It's really bad. But okay, so this right here does not seem to be recursively, right? This is n factorial, but there's no factorial in this definition other than here, right? It doesn't refer to itself. So how can we make this recursive? Well, pretty easily. And this recursive definition ends up being pretty useful in math, especially in calculus, which again, we're not doing calculus, but it is very useful. So we could say n factorial is n times n minus 1 factorial. Right? So it is referring to itself in its definition. So another way that might be a little cleaner to understand if we're not using special symbols for it is if we just call this a function, like fac of n is n times fac of n minus 1. Right? So in order to do the factorial of n, we do the factorial of n minus 1 and then multiply that by n. So let's take a look at what this would look like. Let's go back to our 5 here, right? We already know the answer here based on this definition. It's supposed to be 120. So we're going to say, okay, the factorial of 5, if we look at this definition, it says take 5 times the factorial of 5 minus 1, right? Okay, well, this is the factorial of 4. So, all right, well, in order to compute this factorial of 5, I need to know what is factorial of 4. So, okay, I say, well, let's go do it on the side here. All right, factorial of 4 is 4 times the factorial of 3, right? Because we just take that number and subtract 1 and then repeat. Okay, so now we need the factorial of 3. That's 3 times the factorial of 2. All right, we do it again. Factorial of 2 is 2 times the factorial of 1. All right, we keep going. The factorial of 1 is 1 times the factorial of 0. And we keep going. The factorial of 0 is 0 times the factorial of minus 1. And we keep going forever, right? That seems like a problem. So there's 2 parts to a recursive function. There's this part here, which we call the recursive part, which is the part that refers to itself, right? This is the part, the main meat of our function, right? It's the thing that's calling itself. It's referring to itself. But we need to know when to stop, right? Otherwise, we just literally go on forever. So we also have the stop or base case. So in this case, we're actually given it. As soon as we get to 0, we stop. We know it's 1, right? We also know that factorial of 0 is 1. So that means let's take a look at what we have over here. It means that right here, when I kept going, that's incorrect. This does not happen. We just look at the stop point and we're like, this is where I stop. It's 1. Right? But now that means we can sort of trace our way back up these arrows, right? So factorial of 0 was 1. So that means we can put a 1 there, right? So this is 1 times 1, which of course is 1. But now we sort of rinse and repeat, right? This is a 1, but now this is 2 times 1. So that's 2. And now we go up. that was a 2, right? This factorial of 2 is 2. So then 3 times whatever we just got. 3 times 2 is 6. All right, now we rinse and repeat, right? And this is literally what the computer would do, right? It's going to break it down till it gets to the stopping point, and then it's going to build itself back up. So this is a 6. So now we've got 4 times 6, which is 6, 24. Now we know this is 24. And we're finally at the top where we started. So this is 5 times 24, which is 120. So, okay, this seemingly way more complicated way of doing this produced the same result. Right, so this is just for demonstration purposes, right? Nobody would implement the factorial recursively because it's just so easy to just, you just do a for loop and it's done, right? So this is sort of a bad way to do it, but it demonstrates what's really going on with the algorithm, right? You sort of, in order to do this factorial of 5, we shrunk the problem, right? We reduced the problem of factorial of 5 to the problem of multiplication and factorial of 4, right? And then that needs the factorial of 3 and 2 and 1, and the factorial of 0 is just known, right? We don't have to do any work. So it's this concept of breaking a problem down into simpler ones and then building it back up when you get to your simple case. So recursive functions always have 2 pieces. So we've got this recursive part. This is the part that refers to itself, and it's meant to make our problem smaller. Now, in a technical sense, that doesn't always mean decreasing a number. Sometimes making your problem smaller means increasing a number, but the point is the problem you are trying to solve got smaller. And then we have our stop or base case. And this is, well, it tells us when to stop. Which is important, right? We can't go forever. Because if you went to your computer and just did this, well, I don't even know if Python would even run the code. It might just be like you have an infinite loop and it would just stop it because it's such an obvious infinite loop. But if you were programming in C, it'll let you do it. And then it will probably very quickly run out of memory and crash. But it'll let you do it. So it's important to not have these infinite cases, right? Modern programming languages are usually smart about detecting whether or not you have an infinite recursion. But you know, if you're sitting there and you built something recursively and your program seems to be running forever without any output, you've probably got an infinite recursion. Okay, so this is sort of one that I just constructed, and I think you would probably look at this and agree that the recursive version is worse, right? That's worse than the original definition. But that's generally not the case. Usually the recursive version is simpler to understand and implement. So let's do another example, more math oriented. And this is something that maybe you haven't heard this exact terminology, but it's something that we do a lot when working with like fractions and that sort of stuff. And that's the concept of the greatest common divisor. So the greatest common divisor or GCD, because we like to shorten stuff. So, I mean, the name kind of indicates what it is. It's the greatest common divisor. So we have divisors of numbers, and we're going to take the biggest one of 2 numbers. is the greatest divisor, we'll say largest divisor they share. So that's basically just rewording what greatest common divisor reads as. So we use the notation GCD of A comma B, generally speaking. So in terms of words, this is kind of hard to sort of visualize. So let's just do an example. So let's find the GCD of 12 and 42. Okay, so the naive way to do this, we need to find the largest divisor that they share. So remember, a divisor is something that evenly divides that number. So a divisor of 12 evenly divides 12. So there's no remainder or anything like that. So the best way to do it, our fun little Venn diagram here, and we're going to put divisors of 12 on one side and divisors of 42 on the other. So divisors of 12 and divisors of 42. So hey, what are the divisors of 12?
2, 4.
Yeah, I heard everything. So this one usually doesn't take too long for people to 1, 2, 3, 4, 6, 12, right? It's pretty easy to list off the divisors of 12. 42, maybe. Yeah, so like the way I would do it is I would build a factor tree. Right, so we've got 1, 2, 3, 7, 42, 21, and then we also have 6. And that's probably all of them. I mean, I know it is, but and now we just move it into the intersection when they share them. So they share 1, they share 2, shares 3, don't share 4, they do share 6, and they don't share 12 or 7, and the rest are too big to be a divisor of 12 anyway. So what's the GCD? It's the biggest one. It's 6. So that means that GCD of 12, 42 is 6. Okay, but there's some obvious problems with this already. This is how we found the GCD of 12 and 42. What about GCD of 1,262? And I'm gonna write down there. All right, so based on this, list all the divisors of 1,262, and then list all the divisors of whatever that is, and then find the biggest one they share. Well, 1, that's way too many, right? That's a nightmare. There's so much. And 2, how do you even know you have found all of them, right? Like, you wrote down a bunch of numbers, and then you're like, but did I miss one? I don't know. There's so many. There's like there's hundreds of numbers written down, right? So did I miss one? I don't know, and maybe that's the biggest one. So obvious problems with this. So we like to find an algorithm to sort of capture this idea. So there is a better way. I'm actually going to write this on the side because we're going to come back to it. So this was 1,262 and 5, 1, 2, 6, 3, 1, 2. I just wrote down random numbers. So the better way is what's called the Euclidean algorithm. So we can find GCDs. So we find GCDs using what's called the Euclidean algorithm. So this is defined recursively. So there are two parts to a recursive function or algorithm. We need a stopping point, and then we need the recursive part, right? The part that refers to itself. So the first part is our stopping point. So if we have a comma 0, so that second number is 0, then we're just going to say it's a, right? So that's a stopping point, right? When that second number is 0, we stop. Now, our goal then should be to shrink that second number, right? Make it smaller and smaller and smaller so that we can get to this case. So, okay, if we have the GCD of two numbers, what we can do to shrink it is that first number, we're going to move the second one there. But this, so I'm going to say it out loud, and this is sort of a pop quiz. I need the remainder of a divided by b. So is there an easy way to get the remainder of a divided by b? Remainder of a divided by b. No, that won't work all the time. I might be reaching back far into your Python knowledge. There's a Python operator that will do this. Yes, modulo. So this is just a modulo b. So that's pretty easy to grab, right? A modulo b. And so we see this is definitely shrinking the problem, right? Because if you had, well, in our example here, if you take 42 modulo 12, the remainder of division by 12 is at most 11. Because if it were 12, then you could take another 12 away, and then it's between 0 and 11 again. So this number is always going to get smaller, right? Eventually it will get to 0, just through properties of arithmetic. But the point is, this is our base, and this is our recursive. Okay, so the reason why this ends up actually producing the GCD is, let's just say we would spend at least another class talking about that alone, because we would have to formally define what it means to do division, and then we would have to talk about how remainders work in that division algorithm, and then it's just the point. You can trust me on it. If you don't trust me that this produces the GCD, Wikipedia will bore you with the details. But the point is, it does, and let's do it on this example we just did, just to make sure, right? I'm claiming it works, but you know, we should make sure, right? Like, let's try the example we already know. So we just found the GCD of 12 and 42 was 6, right? So let's find that out. Let's try this algorithm on 12 and 42. So that means we want the GCD of 12 and 42. All right, so what does this algorithm do? It tells us, well, our second number is not a 0, so we do the recursive step, which says move the second number to the first number. And now, here, we need to plug in 12 modulo 42, whatever the result of that is. So this is kind of weird to think about, because what is 12 divided by 42? Not exactly, but like, is that an integer? 12 divided by 42? Are you sure? Yeah, so it's, because this is 12 over 42, right? So this is a fraction, and it's less than 1, right? So the point is, 42 fits in here 0 times, and so what's left over? 12. So all we've done so far is swap the numbers here. And this is actually a common misconception so when I teach this to non-computing people, so like education students or whatever, I just tell them put the biggest number first. You technically don't have to, because all you do, if you go through this algorithm and do modulo and stuff, it's just going to swap the numbers, and now the biggest number is first anyway. So it doesn't matter when you're doing it. Sometimes recursive algorithms will care, and sometimes they won't. So sometimes you have to put the bigger number first or a specific input first, but sometimes it'll resolve itself. And this is an algorithm that just fixes itself on its own. So now we do it again. The second number here is not 0. So we do the recursive step again. And we say, okay, move the second number to the first number. But now we're going to ask, what's 42 modulo 12? So this is the remainder of 42 divided by 12. Well, let's see. 12 is 12, 24, 36. So there is 6 left over when we do that division. So that's the result of the modulo. And now we repeat. We say, okay, what we're going to do is we're going to say, move that second number first. And then we need to ask, what's the remainder of 12 divided by 6? What is the remainder of 12 divided by 6?
7.
Yeah, there is no remainder. Aha! Now we're in this step, right, instead of this one, right? Because now our second number is 0. So when we're in this step, we know we just spit out the first number, right? And it's done. But this does match what we just found, right, through that sort of naive way. So one of the nice things about recursive algorithms, so I kind of mentioned it, is they're really, 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 really easy to implement. So, I mean, you could do this instantly. So here, I pulled up some crappy Python interpreter online. So let's implement the GCD recursively. So, okay, we're going to have our GCD function, right? If the second number is 0, right? That's this right here. Then we just return the first number. Okay. Otherwise, what do? We do that recursive step, right? We say, okay, we're going to return the GCD of the second number moves to the first slot, and then we do the modulo. That's it. Now we've implemented the GCD. So let's confirm this. I mean, this matches literally what's right there, so it's pretty convincing. But 12 and 42, we got 6, right? Okay, that makes sense. But now let's do what are those numbers? 1, 2, 6, 2, and oh god, that one is huge. 1, 3, 4, 5, 1, 2, 6, 3, 7, 2.
6, 3, 1, 2.
6, 3, 1, 2. 2. All right, done. But how many steps did this take, right? So let's ask. So we can just say this is a step, right? So you could do this by hand, and it would have taken 1, 2, 3, 4, 5, 6, 7, 8 steps, and you would have got 2. Oh my god, teams, go away. So you can see that this, like, even by hand, this isn't actually that bad anymore, right? This is an absurdly large number, and it just kind of worked out. I can even make these even bigger. Just match some keys. How many steps did it take? Not even that many. So, like, this is a relatively efficient algorithm. So I hope this convinces you that this recursion is actually useful. Like, the factorial was it's a simple example, but it's one situation where, like, the recursive version was worse. But this, the naive way of, all right, let's just list out all of them, because you could do that as a program too, right? You could implement that, list out all of the divisors and then list out all the other divisors and take the biggest one. That's going to be really, really inefficient. whereas this recursive is just like, it's like 4 lines of code, right? And technically you can shrink it down. You could play Python golf if you want and, you know, make it like 2 lines. If you're a specific kind of freak like that. So, right, you can shrink it down and it's barely anything. So generally speaking though, when you're doing recursive algorithms, you know, you've got your base case, which might involve like a tiny bit of manipulation, but is usually pretty simple. This part here is usually not 1 line of code. It's usually, okay, now I'm in my recursive step. I need to do a bunch of manipulation to my data and then call myself again, right? And shrink the problem down somehow. And usually that's more than 1 line of code, but a point is when you actually have an algorithm written down recursively, it's super easy to implement, right? A lot of them already tell you what you need to do, right? So there's not a whole lot of work in implementing them. And actually, we can do the factorial too using this. Again, it's a bad way to do it, but same exact idea. So it would be back of n is if n is 0, return 1, else return n times, boom. So then you could say print, and this should give us 120. Let's see. And so this is a perfect example of what I mean of the downside to recursion, is you can very easily run out of memory and stuff like that. So you have to be careful with it. You have to make sure that you're using it in the right situation. By the way, Python already has a factorial implemented. It's just an exclamation mark. Okay, so I have one more example that sort of, I'm going to call it academic in the sense of it's meaningless. It doesn't do anything. It's just I invented it for the purposes of an exercise. But we'll just go through it so that I can sort of really drive home how these sort of trace through the algorithm. So define a function. So here, our second number is 0. We're going to say it's -1. But we actually have an extra condition here, and there's nothing wrong with that. So what this is saying is, hey, if the 2 numbers are the same, then it's 2, right? If they are the same thing, which means if they are different, so this here is our sort of base, right? This is our stopping point. So now we need a recursive call, and I've chose n and k as the variables here, but the point is they're different numbers, right? If they're the same, we're already in this case, but if they're different, then this is what we need to do. So we're going to say it's 3 times, and now we do our recursive call, n minus 1, k minus 1, minus 2 times f of n minus 1, comma k. So this is saying, all right, do 3 times the call of the function where you subtract 1 from each variable, and then also minus 2 times that call again, except you only decrease the first number by 1. You leave the other one alone. So let's compute. What did I choose? F of 3 comma 2. Okay, so we're just going to go through the steps here. So, random question. Is anyone here colorblind? Okay. I don't use colors for like any specific reason other than potentially drawing emphasis, but this is one of those situations where I have multiple colors, so if someone was like, I'm red-green colorblind, then I'd be like, okay, I'm not going to use red and green, then I'll use 2 different colors. But if nobody cares, then I'll just pick the 2 colors that I have open. Which again, this is just for emphasis purposes. It's not actually fundamental. So this is what we're trying to compute. So what it says is these are different numbers. So we're in this situation, right? We're in the recursive step. So we're not doing that yet. So what this says is take 3 times f of, now I take my first number and subtract 1. And then I take my second number and I subtract 1. Minus 2 times, again, my first number minus 1. But now my second number, I just leave it alone. Right? So everything there in black is from this, but is not a variable. Right? The stuff in blue and red, those are my variables that are being passed along this algorithm. Okay, so what does this actually look like, when we actually figure this out? So this is f of 2, 1 minus 2 times f of 2, 2. Okay, well, now we need to break this down, right? We need to ask ourselves, okay, if we want to compute this, we need to figure out what is this and what is this, right? What is f of 2, 1 and what is f of 2, 2? Because once we know those, we can sort of plug them in here and work out our answer. So, okay, over here, I'm going to say, all right, we've got f of, use the colors again, 2, 1. And over here, we have f of 2, 2. Okay, now I'm going to go through this the same way a computer would. Well, asterisk. Modern compilers are smart. They can detect recursion and save some memory and space. But we're going from the left to the right. This is the first one we see. We're going to do this. Right? We've got f of 2, 1. We need to figure out what this is. Well, we look at this. Different numbers, right? It's 2 and 1. So that means we need to do that step again. So this is going to be f of, so it's 2 minus 1, 1 minus 1. Sorry, there's a 3 in the front there. Minus 2 times f of, similar idea, 2 minus 1. And we leave this one alone. All right, so what does this look like? 3 times f of 1, 0 minus 2 times f of 1, 1. All right, so again, we need to figure out what these are. But we're in good shape here because f of 1, 0, we're in that situation where the second number is a 0. So we're actually in this case. So this is minus 1. Same thing here. We're actually in this case, the two numbers are the same. So this is 2. So now that means we can actually start working our way back up this tree here, right? So this is minus 1, and this is 2. So this whole thing then is 3 times minus 1 minus 2 times 2, right? So this is 3 times minus 1 minus 2 times 2. I'm going to have to move this over. Okay, but that's easy to do. This is minus 7, right? So we just found this answer is minus 7. But that means this part here, up this arrow, is minus 7. Cool. So this is 3 times minus 7 minus 2 times, great, we've got more, right? So now we have to figure that out. But this one's not too bad because we're in this case. So it's 2. So we don't have to go any further. But it's possible that we could have, right? It's possible that this is also something that we need to break down into a bunch of steps. But the point is, this is 2. So up we go. So now all told, we've got 3 times minus 7 minus 2 times 2. So all told, that is minus 21 minus 4 is minus 25. And so then that means over here, we could say f of 3 comma 2 is minus 25. So this is an accurate portrayal of what your computer does, again, with an asterisk. It's going to take the first function call it sees in this recursive part, and it's going to just break it down until it can stop. And then, you know, this is what we're returning, so it builds up, right? And again, this is another example of something that's really easy to implement into Python, right? As it's written, f of nk, oh boy. So if k is equal to 0, return minus 1. Otherwise, if n equals k, return 2, else return 3 times f of n minus 1, k minus 1, minus 2 times f of n minus 1, k. Print f of, what is it, 3, 2? And we better hope this works, otherwise that'll be embarrassing. Minus 25, right? So, again, pretty easy to implement. Can I change this? No. So we just literally read off the algorithm, right? We didn't have to do anything extra to implement this, right? That's one of our base cases. That's another one, and then that's the recursive step, right? And then boom, algorithm's done. Now, I don't want to misrepresent recursion. It is not always this simple. Again, if you want to see examples of it because you're curious, merge sort is a recursive sorting algorithm that you can probably understand with like an intro Python course, which you have. So you can go look that up if you want to see an example of a recursive algorithm that's like actually got some meat to it and is actually useful. Like the sorted function in Python kind of does a little bit of fuzziness at first, and then I think it does probably merge sort because it's n log n algorithmic efficiency, so it's pretty good. I don't know which one it does, but it's probably that. Anyway, good news. I have a gift for you. It's math. It's quiz. It's literally, I made the quiz and this example at the same time. I literally just changed, like, I think I changed this. Like, I think the quiz is, it doesn't have this. This is a plus and it doesn't have that. So like I didn't have to work. I didn't work very hard to make the quiz. You can basically follow what we've done here to get through the quiz. But any questions on recursion, or is it? It's one of those things where once you actually sit down and try and unpack it yourself, it's not as bad as you think it is. But when you're just staring at someone doing it, you're like, wow, that's a lot. So I get it. I learned